Welcome to our webinar, Optimizing Motion Control System Design through Component Technology Analysis. Or, more succinctly, a motion system is more than the sum of its parts. Hi, I'm Art Holtzknecht, the Engineering Manager at HIWIN Corporation. We're a leading manufacturer of precision automation components and mechatronic systems. We're located in Huntley, Illinois, in the Chicago suburbs. I'll be your presenter today. Let's discuss what we're going to talk about today in this webinar. First, let me say that this is an overview presentation. It's a survey of some of the key concepts and component technologies used in motion system design. Each one of these topics can be a full webinar on its own. So for an in-depth discussion on these topics, please contact us at HIWIN. We'd be happy to work with you on your motion application. What we'll talk about today is, what is a motion system in the context of this webinar specifically? Motion system is a broad term, can comprise a lot of things. We'll look at how do we specify and characterize motion systems? What's some of the key terminology that motion system design engineers use? And how are those terms defined? We'll look at different XY stage configurations. Then we'll go from theory to practice. How do we actually characterize these motion systems in the real world? The next part of the webinar will be how we put the various pieces together. So we'll look at the motion system components, the elements comprising a motion system. We'll look at drive types, linear motors, ball screws. We'll consider open loop or closed loop operation using stepper motors or servo motors. We'll look at feedback encoders. That's a critical component. We'll look at incremental or absolute, direct or indirect feedback, and whether they are linear encoders or motor mounted rotary. We'll also look at the choice of materials that we use. So whether we use aluminum, steel, granite, composite, there's a wide range of materials that are used and they have different characteristics. And then finally, we'll look at digital servo drives and we'll look at field bus architectures and how control loops influence the behavior of a motion system. But first, let's start with the motion system design process. Understanding the application requirements is the key. Really what we want to do is identify what is the most important spec or specifications. And we want to focus there. Once we know that, then let's consider the best axis configuration that will meet the objectives. And from there, we'll determine an error budget. That is, how much error contribution is allowed from each axis in our system. When we talk about a motion system in this webinar, we're really referring to a complete positioning system that consists of a mechanical system or a mechatronic system with the structural mechanics plus some type of drive elements and some feedback elements, the servo drives, which are the electronics that power the system, and ultimately of the motion controller, which will coordinate the motion of the various servo drives. Vertically integrated motion system suppliers, we understand that each of the component technologies and how they can combine to create an optimized design for an application. So when a complete solution is provided, there's no opportunity for finger pointing when the system doesn't meet a particular specification. You have one source. Also, compatibility of all the elements is ensured. They're guaranteed to work together. And testing the overall behavior as a system provides the most reliable indicator of performance versus testing the components individually. So let's start with the mechatronic elements, the stages. Linear stages come in lots of configurations. So from a single linear axis, you can combine them in a lot of ways to create XY motion. Let's discuss a few of the possibilities. So the stacked XY stage is probably the most common. It's, you typically just take two stages, stack them perpendicular to one another. You can also add a rotary axis or other axes for additional motion, XY theta or XYZ. Another type design that's common is the split axis design. This design is space saving and offers some potentially higher accuracy because you can decouple the axes from each other. However, it requires a structure to support it. Another configuration is the cantilevered XY or XYZ. In this type of design, the workpiece is usually stationary and the process tool moves above it. It's a lower cost system approach, but it does have some limitations for longer travels. When we need large workpieces or longer travels and a cantilever configuration isn't really feasible, the gantry is often a better alternative. A stationary workpiece in this case can be very large and very heavy because it's not moving. It also works very well with a conveyor to load parts, and very large travels are possible. But one drawback of this approach is it does require an extra axis, the X1 and X2 axes, which are a pair that must be precisely synchronized by the servo drives. At the upper end of the performance spectrum, air bearing systems. Air bearings offer the highest possible accuracy. A single plane air bearing stages gives you the best possible geometric performance, but at a price. They are an expensive solution. However, they are ideal for high-end semiconductor and life science applications where the ultimate performance is needed, particularly in terms of accuracy and geometric performance down to the submicron level. However, it also requires a clean environment and a supply of clean and dry air. But if you need the best possible performance and you have the budget for it, you can't go wrong with an air bearing stage. Now, in addition to the configurations, motion systems requirements vary widely depending on the type of application. They can go from microns to nanometers. You might have an application in general automation, or maybe a precision positioning, laser material processing, or something like that. Or maybe you are operating in that ultra-high performance realm of semiconductor metrology or genomics and drug discovery. Experienced motion system suppliers will offer these different types of stage designs to provide optimal solutions at the best price-performance ratio for the application. So, with all of this, how do you choose? Well, let's look into the key ways to specify a motion system first. So, if we look at some basic characteristics of a motion system, perhaps footprint, which one is going to be the best to minimize AB errors? AB errors, what are they? Stay tuned. We're going to get to that in detail because they're critical to performance. Suffice it to say, we want to keep them to a minimum in our designs. What about our workpiece? Is it large or is it heavy? Do we require long travels? Do we have a high-speed system? Or is cost the most paramount? Cost is always a factor, but really where does it come into play? All of these different characteristics and many more help us to narrow down what type of axis configuration we want to consider in our design. When we start looking at motion axes, one of the most important things we start out with first is, and have to understand conceptually, is the 6 degrees of freedom of every axis. Every linear motion axis, as well as some of the components, for example, a linear guideway, has 6 degrees of freedom. And really fundamentally, the goal of precision motion system design is to control one, which is our desired direction of motion, and you want to minimize the other 5. It's important to understand you can't make the other 5 0, but you can minimize them. So as you build a motion system from its components, these error sources contributed by each of the components adds together. So if we look at the 6 degrees of freedom, what are they? Well, there's the desired direction of motion. In this case, we'll call it Z. But then there's 5 other components of generally undesirable or unwanted motions. They would be horizontal and vertical straightness, so deviations from the straight line motion. And then there are 3 angular errors, pitch, yaw, and roll. And those are rotations about each of the axes. And those are the ones that really add up, and they're the ones we really want to try and minimize, because those are especially what contribute the most to AB errors, because they are positioning errors caused by deflections, angular deflections in the motion system. And experienced motion engineers, we know how to design motion systems to minimize those errors. And when you analyze all the errors in a multi-axis system, it starts to get really complicated, and we'll talk more about that in a few moments. But all of those components are used to form the error budget. Here's another illustration of the 6 degrees of freedom. Again, anything other than straight line linear motion results in positioning errors in the overall motion system. So here we can see the travel along a linear guideway bearing. So you can see the desired direction of travel, linear. You see horizontal straightness and vertical straightness or flatness, and then the 3 angular components of errors, pitch, yaw, and roll. When we build an axis from these components, that axis itself also has 6 degrees of freedom. Linear stages have errors that are the result of the combination of the component tolerances used to build the stage. And what happens is you end up with some uncertainty in your working position due to your geometric errors. You may have the ideal position, but these deflections and deformations will result in some errors. So it's getting really complicated when you combine the axes in a motion system. The geometric errors combine statistically. Each axis has its own 6 degrees of freedom. Plus, there's another term, the orthogonality, otherwise called perpendicularity, or sometimes just a squareness, how well we align those axes together. So how do you combine them? How do you add them all up? Well, we may think the best way is just add them all up algebraically. Give me my worst case. That is overly pessimistic. It's also unlikely to occur. All the errors aren't always going to go against you in the same way. And ultimately, it results then in an overly tight system specification in order to minimize them. And that drives cost. What motion engineers do is we add them statistically. An RMS, or root mean squared calculation, is the accepted industry method, and it's a much more realistic estimate of performance. And this is really the foundation of the error budget. In other words, how do I predict the motion system performance at my tool point, or my ideal working position or point of interest? Let's look at three key terms that are used in motion industry a lot: accuracy, repeatability, and resolution. These are kind of the big three specs in motion system. They are independent parameters, but they're often erroneously used interchangeably, but they each have a specific meaning. We're going to discuss each one of these in detail because they are important. But suffice it to say that you can have high resolution and high accuracy, or you can have low resolution and high accuracy, and vice versa. Don't assume that a high-resolution motion system also means it's accurate. In terms of cost, accuracy is the most expensive parameter to achieve. Resolution is often the least expensive. Resolution is simply the smallest increment of information in the system. If we look at these targets, here's a good graphical way to sort of illustrate the different concepts of accuracy and repeatability. In the upper leftmost one, we can see a system that is not accurate and not repeatable. We can't hit the bullseye and we're all over the place. Not a very good motion system if that's what our goal is. On the upper right, we have a system that's also not particularly accurate. We can't hit the bullseye, but all the points are clustered together. This system is highly repeatable. And an advantage of a repeatable system is that if we look to the next slide, the lower right-hand target, you can see that repeatable systems can sometimes be error mapped. If all of the points are clustered together, we can do a type of calibration, perhaps, to improve the accuracy. And then finally, in the lower left, we have a system that is accurate and repeatable. Without any type of compensation, we can hit the target every time. This is the most expensive type of system to manufacture. So we really need to consider carefully in our application, is it repeatability that's needed or is it true accuracy? That has a very big cost impact. Let's look at the three terms again: accuracy, repeatability, resolution. Again, they're the key terms in motion system specification, and they are used interchangeably, but that's not the correct method. They each have specific accuracy. It is the ability to get to a target position within a defined tolerance. An important element of accuracy is that it should be traceable to a measuring standard that's calibrated. Because if we say a system is accuracy, well, we say, well, how do you know? Well, it's been measured with an instrument that I happen to believe is more accurate than the system I'm measuring. Otherwise, which one do I believe? That's the concept of traceability. If we use a gauge, that gauge should be calibrated. But then you say, well, we get to the chicken and the egg problem. How do you know that gauge that you use to calibrate your gauge is good? Well, it's calibrated to an even better gauge, and ultimately to an even better gauge, all the way back to the National Institute of Standards and Technology, or NIST, where they are the final arbiter of dimensional accuracy. That's called traceability. If your measuring instrument can be traced back to the accepted industry standard. Important thing because of that is that high accuracy is expensive to achieve. And consider if repeatability is really needed. Oftentimes it is, and that saves cost. Repeatability, that's the ability to return to a previously achieved position within a defined tolerance. It's a statistical value intrinsically. It represents the uncertainty of achieving a target window. And the important thing, again, is that highly repeatable systems can be error mapped to improve their accuracy. You can compensate or calibrate those systems. What about resolution? Resolution, again, is the smallest increment of position information in the system. It's also the smallest programmable increment of motion in a servo system. But just because you can program it doesn't mean you're going to achieve it and you're going to make that kind of motion. And in a digital system, there's no information below the resolution. The information is said to be quantized. In this example here, this illustration, is a tape measure, common tape measure. It has a resolution of a 32nd of an inch. That's the finest tick mark. But we don't know how accurate it is. How well made is this tape measure? Is it a really expensive, high-grade, calibrated one? Or is it a low-cost one that we bought at the local dollar store? Accuracy and resolution are not the same thing, and one does not imply the other. Another important concept is how we make our measurement. Is it direct or indirect measurement? In the feedback system of a motion controller, you can provide a type of encoder. A linear encoder is a device that provides a direct measurement of the payload's position. It's the most accurate method to measure position. Why? Because it's measuring directly. You don't have any intervening elements in between that are introducing errors in that measurement. The quality of the encoder and the specification of it in and of itself is important. but you don't want to add more errors to your encoder measurement. An indirect measurement, that requires a conversion factor. So you do have intervening elements to determine a payload position. For example, if you've got a ball screw system and you put a rotary encoder on it to measure it, well, your payload position is basically a function of the encoder counts and the lead of the screw. How many millimeters per revolution do I get? And these are subject to errors due to deflections, inaccuracy in the lead of the screw itself, its manufacturing tolerances, wind up, etc. Another important thing about encoders generally is that they can be either incremental or absolute. Again, accuracy is not really related to whether it's an incremental or an absolute encoder. Incremental encoders are the most common. They provide relative motion from a defined starting point or a datum. Therefore, incremental encoders require some type of initialization, often referred to as homing, upon startup. Common terms you may hear when people are talking about incremental encoders are A quad B encoder or TTL or square wave. Generally, those are all referring to incremental encoders, and they're just commonplace terms that are used. An absolute encoder, on the other hand, it provides a direct reading of the position. It outputs a digital word using a protocol. Homing isn't needed. The encoder knows exactly where it is immediately upon power up. Common terms you might hear when people talk about absolute encoders or NDAT encoder or BIS encoder. These are actually describing the protocol used. So it's important to verify that the drive that you're selecting, the servo drive, supports the encoder protocol to ensure compatibility, make sure they can communicate with each other. Let's return now to the subject of ABI errors. You remember we spoke about those earlier in the presentation, and we emphasized how minimizing them is an important parameter. Well, one of the first things to understand about ABI errors is that an encoder in a motion system provides correct positioning information only at the point of measurement. So for example, here with a linear encoder, it's going to be where the read head is located. Now, the point of interest in our process, which is often referred to as the tool point, is going to be located some physical distance away from the encoder. It has to be just because we have components in the way and our workpiece and that has some dimensions. So any deflections that are occurring in the motion system, and remember again, those 6 degrees of freedom, they will result in errors at the tool point. So deviations from where the encoder thinks the tool point is versus where it actually is. And those ABI errors are the most troublesome. Why? Because they amplify by that offset distance. So the distance between the tool point and the measurement point multiplied by the sine of the offset angle equals your ABI error. So let's take one simple example. If I'm 100 millimeters away from the encoder, which is very realistic if you think about just the components that have to get in between the encoder and the tool point, and I have an angular error, let's say a pitch error, on the order of only 5 arc seconds, an extremely small angle. In many cases, it can be significantly larger than that. But that in and of itself will result in 2.5 microns of ABI error. So even if my encoder is perfect, I'll still have 2.5 microns of error between my encoder measurement and my tool point. Looking at the next slide here, we can see how this might manifest. So if we move the axis from a nice uniformly supported center position and we move to the extreme of travel, we're going to get some deflection. Here it's kind of exaggerated, but the idea is it's still going to occur. And as it's moved, you can see now 2 sets of dashed lines. The green line represents the encoder position, and the red line represents the ABI error or the deflected position. If we zoom in, we'll get a little bit closer look at that. So here's what happens. The linear encoder read head is still reading exactly where it is. It's reading just fine. But that deflection has meant that the tool point, our point of interest, is shifted by that deflection. So this is only one of those errors that we're illustrating here. Remember all the others. You've got pitch, roll, yaw, straightness, flatness, orthogonality. All of those are contributing. They all add up very rapidly. So it's very important to work to minimize them because especially ABI errors in particular, they add up, and again, they're amplifiers. The further away you get, the larger they become. So now that we understand some of the contributing error sources and what they are and how we define them, how do we measure our actual motion system? How do we know that the system that we are working on is actually meeting the specifications that we've designed? Well, motion engineers use industry standard techniques and measurement protocols and instrumentation to verify system specs. One of the most common tools for this purpose is the laser interferometer. It's a rather expensive but extremely precise instrument. It's using the wavelength of a laser light, which is very precisely known and is fully traceable back to NIST. And it gives you the positioning accuracy and the repeatability, but also by different optic designs, you can measure the other stage geometric errors. So you can measure those other degrees of freedom. So a benefit of working with an experienced motion systems company is that they will have these instruments and they'll know how to use them, because proper setup of the optics is critical to getting good data. And ultimately, these tools provide the performance test data in an easy to understand report so that you can see exactly what kind of behavior you're getting. And then you can use that data to error map or compensate your system. So now let's look at the elements used in motion systems. Let's look at feedback types. We talked about them earlier a little bit, and direct and indirect measurement. Starting at the bottom of the slide, indirect measurement. Open loop systems, for example, with a stepper motor, they don't use feedback at all. They're very low cost, but they do suffer from lower accuracy and repeatability. But they're a good choice for simpler, low precision applications. You simply send a pulse train of steps to the stepper motor and it moves a predefined increment in response to each step. The thing is, you can miss steps, and you have no way of knowing did you get to the position that you want. You're trusting that all your components have the right tolerances, and you're going kind of blind. What you can do next is you can add a servo motor instead. Take the stepper off and put a servo motor with a motor-mounted encoder on the back. Now you've got what's called a closed loop system with feedback, and that will give you higher dynamic performance and also better accuracy, because now you're measuring. But you're still only measuring where the motor shaft is because it's coupled to the motor. You will have wind-up and deflections, and you're inferring or indirectly measuring where your payload is. A linear motor with a linear encoder is the highest performance solution. Your speed, your accuracy, your dynamic behavior will all be better, because you're measuring directly. So you would have a linear scale and a linear encoder read head mounted in direct measurement of the position of the payload. But again, you will still have ABI errors because that encoder read head is not exactly where your tool point is. So those deflections are still going to exist. Now, in an indirect measurement system, like a ball screw drive, you can also improve its performance by adding a linear encoder. In that case, you have often what's called a dual loop servo, where you use the motor feedback to stabilize the servo loop for the motor, and then you have an outer positioning loop to measure from the linear encoder and determine the payload position directly. Now let's look at the bearing types that are used in motion systems. So there are many different choices available, so we're only going to focus on a few of the more common ones. Let's first start with the crossed roller bearing. Crossed roller bearings consist of alternately crossed, precisely machined cylinders that ride in a precision ground pair of V-grooves. And they can be either linear or rotary, both types are commonly found. And they provide very smooth motion because of the rolling, non-recirculating bearings. They also can be very accurate because the machining tolerances on the V-grooves can be controlled to extremely tight tolerances. Another type, perhaps the best overall choice for many applications, is the recirculating linear guideway bearing. There are many configurations and different options that are available that make choosing an optimal linear guideway bearing an easy decision in many cases. So the linear recirculating ball bearing linear guideway has a bearing block that rides on a precision guideway. It can be either with ball bearings or, for heavier load capacity, roller bearing versions are also available. They can have very long lengths. You can put the guideway bearings can be joined together to essentially unlimited travel length, and they provide excellent load capacity. Another choice is the ball spline. Ball spline is also a type of recirculating linear guideway, but it's unique in that it can also transmit torque while allowing for linear motion. So by rotating the shaft, we can transmit torque, whereas the linear motion is provided by the ball bearings that are recirculating. Let's focus a bit on the recirculating linear guideway bearing because, again, these are the most commonly used these days, and they are an excellent choice. They're really versatile. You can get very high stiffness from them. You can get excellent accuracy. Load capacity can be extremely high, and you can get a very long service life out of them. Tens of thousands of kilometers is possible. In the linear guideway, the bearing blocks, which are compact, they move with the load. So the reaction of the bearing load to the payload is constant. And you can have multiple bearing blocks on the same guideway, and you can have multiple sets of guideways to uniformly support your load. They're available in a wide range of sizes and styles, from miniature, only a few millimeters in size, all the way to very large, very heavy duty supporting tens of kilonewtons. They've been around for a long time, and the designs of linear guideways are highly optimized. So you can choose the performance characteristics that are necessary for your application specifically. For example, they're available in a wide range of accuracy grades. You can adjust the preload to get different stiffness or friction. Different lubricants are available for different unique environment conditions. For example, perhaps you're in a clean room, maybe in a vacuum, or perhaps you're operating in a high temperature. Also, different types of sealing are available. So you can be, for example, operating in a dirty or a harsher environment, and you might need extra sealing. You can have pre-lubrication options as well. All of these are widely available in the recirculating linear guideway product offering. Air bearings are another option, but again, due to the cost and complexity, they're only economically viable for the highest performance system. Recirculating linear guideways are the most common. So here's just some typical characteristics that we may need in our motion system. Are we looking for accuracy, friction, smoothness, low maintenance? We need high stiffness, long life. You can see what are the relative merit of one versus the other. Big thing is recirculating linear guideways are often going to be a good solution for performance and oftentimes the lowest cost solution. Air bearings are excellent for performance, but they are expensive. Let's look at the type of drive or motor drive that we provide to our motion system. Linear motors are often used because they offer many advantages over other drive systems for precision motion. A linear motor is a direct drive. Just like we have direct feedback and indirect feedback, we can have direct drive and indirect drive. In a direct drive, the payload is directly coupled to the motor. What this means is you get very high servo stiffness and servo loop bandwidth. You can achieve really high speeds, 5 meters per second or even more. You don't have any backlash or friction coming from the motor. It's directly coupled and there is no lost motion. So you can achieve very high accuracy. The motor itself is not going to be a limiting factor in achieving system accuracy. A linear motor is often your best solution for very smooth scanning with low velocity ripple, especially an ironless type motor, which we'll talk about. One thing to consider is if you do use a linear motor, you will need a linear encoder for position feedback, which adds some cost. Linear motors have been around for a long time, and they come in quite a few different configurations and force ratings. The iron core style is what you would typically consider for the highest force density. The iron core provides a focusing of the magnetic flux, and that means for a given size you get more force output. So that makes the iron core motor ideal for high-speed point-to-point applications, where if I need to get from A to B in the fastest possible time. However, the magnetic attraction of the iron in the core of the motor to the permanent magnets in the stator does result in what's called cogging or some ripple, a magnetic detenting force. Modern digital servo drives will offer some cogging ripple compensation to help smooth it out. But really, if you need smooth motion, an ironless motor is going to be your better solution. It offers the smoothest motion because it has no magnetic attraction, or sometimes referred to as magnetic preload. The lack of iron in the motor means there's no cogging at all. This makes it ideal for scanning applications and lighter payloads. However, because it doesn't have iron, it doesn't have something to help focus the flux, so they generally are lower forced motors. The best solution if you have an air bearing system as well, because that magnetic attraction can put quite a high load on the bearing, and air bearings themselves are not particularly capable of high loads. Another type of ironless motor is the tubular shaft motor. That gives it a unique form factor that is sometimes suitable in designs, and they tend to be ironless. Iron core versions also can exist, but most often they're ironless. And you can move either the shaft or you can move the moving coil. The coil can move. And that's the case with all linear motor types. You can move either the magnets or the coil. Linear motors enable multiple carriages on the same structure. So that's a unique characteristic of a linear motor. You can have 2 or more carriages on the same base, and they can be positioned completely independently. So this saves you space and cost. They share a work envelope, so you have to be careful to make sure that you don't program them to crash into one another. Absolute encoders help for that because they always know where they are, so you can easily manage anti-crash logic in the motion programming. These are ideal for pick-and-place applications or high-throughput processes. They save space, and they are very economical. Here you see an example configuration with 2 carriages on the same base, each one supporting a separate z-axis, and each of those z-axes are using tubular shaft motors. What about rotation? We don't always need linear motion. Sometimes we need rotation. In this case, torque motors are often used. A torque motor is a type of direct drive. Often these are employed in rotary stages, rotary positioning tables, and analogous to linear motors, a torque motor positions the load directly without any intervening couplings or gearing, so it is a direct drive. This gives you very high servo stiffness, you get fast moving cell, you can get smooth scanning, you have a direct coupled feedback encoder, so that provides high accuracy capability. You don't have any backlash or any gear wear, so the system has very long life, and you get really direct drive and direct measurement, which is the best possible combination. You can't always use a direct drive. Ball screws are preferable for certain applications, for sure. They're ubiquitous in the precision machinery industry. It's far more prevalent than linear motors, and there's good reasons for that. When applied correctly, a ball screw can provide years of reliable service and excellent performance. They're really the best choice for widely varying payloads, because they are indirect, and you have the phenomenon known as reflected inertia. In other words, the load that the motor feels is proportional to the square of the lead of the screw. Also, a ball screw doesn't require an expensive linear encoder. You can use a motor-mounted rotary encoder, and that's a good solution for a lower accuracy, lower cost solution. And they've been around for so long. I mean, there's a huge variety of sizes and leads and load ratings and accuracy grades. Generally, rolled ball screw threads are more economical. Precision ground ball screws are higher accuracy, and they're also a good choice for the highest precision, where you can get the most accurate leads. If we look at some comparison specifications of how we might drive a decision from one type to another, on the left-hand side column, we have some typical characteristics that we might need in our motion system, be it accuracy or backlash or hysteresis, another term for backlash. We need smoothness, again, low maintenance, high frequency response, small step size, or maybe high speed. Or maybe we just need to hold stability. We need to hold very still for imaging or some other process. Are we running vertically? Ball screw is ideal in a vertical application. We can apply a brake to the motor very easily to support that payload. A linear motor, you're going to need a counterbalance. One nice thing about a linear motor, you can go very long travels. In fact, there's really no limit. And then you look at your environment. Is it a dirty environment or a clean environment? And then cost, of course. A linear motor in and of itself is not more expensive than the other choices, but because you need a linear encoder, that needs to be considered in total system cost. Another type of drive is the belt drive. We're not going to really dwell on it here because they're not really used in high precision motion systems. It's less precise than a ball screw or a linear motor, but it's worth considering for certain applications. Low cost, low accuracy mainly, but they're very good for high speed as well, and they work well in dirty environments. Now let's consider one of the most important elements. What materials do we use to construct our motion system? Choosing the right materials is very important. What are some of the things we look for when we want to choose a material? Well, stiffness. How stiff is the material that we're going to use? We want to minimize deflections under load and the resulting Abbey errors. We want the material to exhibit good damping properties. We want it to reduce vibrations and which enables faster settling. We want it to have a high natural frequency so that we can keep resonances outside the excitations induced by the motion system, particularly in direct drives like linear motors. We want the material to be thermally stable. So we want to consider its coefficient of thermal expansion and also its thermal conductivity. Is it an insulator or a conductor of heat? Also, what's really important is to pay careful attention to the mechanical tolerances on machined parts and the components that we use. We don't want to over-specify tight tolerances. That adds extra cost. On the other hand, too coarse of a tolerance can deform other parts, ultimately reduce the overall performance. Vibration damping is really important, especially in high dynamic systems, such as those using linear motors. Because the linear motor is capable of such high dynamic performance, it can induce high frequency vibrations into the machine structures. Vibration damping is an important characteristic to consider in this case. Vibrations can also come from external sources, nearby heavy machinery, or road and rail traffic, for example. Polymer composite materials, you can see, are the best in terms of damping overall, but they require a mold, so they're really only suitable for high volume production applications where the cost of a rather expensive mold can be justified. However, you can consider a hybrid structure. For example, a steel profile, which is high stiffness, can be filled with polymer composite, and you can get sort of a combination of specifications. The thing about stiffer materials is they'll have less initial deflection to an impulse or a disturbance, but they may ring for a long time, and that will show up in the settling time and behavior of the system. Here's a brief comparison table of different materials that are often used in precision machines. So we have on the left-hand side a list of materials, commonly used materials. And then we have some parameters, the Young's modulus or the stiffness, how heavy is it going to be? And we want often lightweight structures. The thermal conductivity, is it an insulator or a conductor? And its thermal expansion, does the material expand a lot or a little? So you can see that there's not one obvious choice that is best in all parameters. There are some unique materials that are specially engineered for precision engineering. You'll notice a material called Invar or a material called Zerodor. And the reason those are chosen is if you look on the far right-hand column, again, thermal expansion, look at how small that number is. Compare it to, say, aluminum and Zerodor, you get a huge difference. So if thermal expansion is an important characteristic, you've got a varying temperature, for example, you may want to consider using Zerodor, but it's not a very good structural material. It's actually a type of glass ceramic. So use materials judiciously, work with an experienced motion system supplier who can help identify which materials to use where and how they should be deployed in the motion system design. Now let's get to the electronics that are used in our motion systems. The servo drive does two things. It provides the electrical power to the motion system. So it's how we convert electrical power to mechanical motion. It's also the brains of our motion system. There's software and firmware running inside the drive that provides the servo loop closure and helps stabilize and generate performance. The nice thing about servo drives is they are improving rapidly because of the advances in computing technology. There's a lot of specs to consider when picking a servo drive. Far too many to go into detail here in this webinar. So it's important to work with your motion supplier to ensure that the drive is compatible and it has sufficient power for the application. One thing that's really important to consider is that most modern drives are used in field bus architectures. So you may have heard of these, the EtherCAT, which is very popular because it's interoperable. Lots of devices run on an EtherCAT. Others include a Profibus, Modbus, CAN bus, Ethernet IP. So if you're going to use a field bus architecture, of course, you need to ensure that the drives that you're using have the appropriate interface for that field bus. Now, the digital drives that are out there in the market today have a lot of different tuning parameters, lots of adjustments, ways to optimize the behavior of a system. It can be daunting, but some of the advances in computing technology mean that they often include an auto-tuning algorithm that you can use, which will often achieve quite acceptable performance with no need to manually set all the parameters. You might need to tweak a few, but it really reduces the need for servo expertise. You don't need to be a controls engineer that's been studying control loop and dynamics for years and years in order to get a good performing servo nowadays. Used to be the case years ago, not anymore. Also, to make it easier for us out in the field trying to do motion system design, is there's modern servo sizing tools that enable the calculation of motion profiles, and they help you to specify the optimal stage and the motors. So these tools reduce the expertise needed to size and specify the components, and manufacturers will often make them available for customers to use. However, it's always recommended check back with the experts to verify the selection, because it's important to understand that these tools are providing an idealized view of what the system will do. The behavior of the real system in the real world will be different. And one of the things it does depend heavily on is the quality of the servo loop control. So we may specify and design a really beautiful trapezoidal profile in a sizing tool. The actual behavior of the system, it's going to approximate that and be very close to that. But those real world impacts, friction, deflection, stiffness, resonance, all those things are going to come into play, and they're going to influence the behavior and cause deviations from the ideal. In particular, let's look at even how optimized tuning can make a big difference in behavior. On the right-hand side, you see 3 pictures of servo loop performance to that trapezoidal profile. It's all the same system. The only difference is how the parameters were specified and tuned. If it's poorly tuned, you can see ringing and oscillations. The system never calms down. That's wasting a lot of energy, generating heat as well. An overly damped system can result in sluggish performance. You can put a very nice high-performance linear motor, but then if you tune it so much that it's detuned, you're not going to realize the benefit of that linear motor's performance capability. But if you optimize that tuning, you can get quick move and settle, no overshoot, rapid performance. You can also optimize for scanning, for low ripple. So you can use notch filters to remove unwanted frequency disturbances so that the servo itself does not provide output into the system that excites those resonances. So there's a lot of sophisticated features in modern drives. And also, if your servo is well tuned, it's going to quickly stabilize and it's going to reject those disturbance inputs. So here's just an example of a real system, and you can see some disturbance impulse in the left-hand graph, but you can see it rapidly stabilizes, and ultimately in this particular case, it's holding stability of 40 nanometers or 0.04 microns. So a well-designed system and a properly specified servo with optimized tuning, you can get outstanding performance. And this is what's really important in modern motion system design. And working with the experienced motion system suppliers that are out there in the industry, they can help you design a system, choose the right parameters, work within your budget, and give you the performance and predict what performance you can expect and measure it and prove it to you. So with that, we're going to conclude our webinar. Do appreciate you for joining us for this, and thank you very much, and we do look forward to hearing from you.